Ever looked up at a sunset and wondered why red? Or pondered the sky's blue expanse?
Yeah.
Today's deep dive takes us into the fascinating physics of it all, guided by, well, none other than Richard Feynman.
Oh, Feynman. He had this knack for, making even complex topics like quantum electrodynamics feel almost tangible, wouldn't you say?
Absolutely.
We're diving into excerpts from his lectures on physics, specifically Volume 1, Chapter 32, where he tackles light, radiation, and color.
From what I've read, he had this uncanny ability to connect, seemingly unrelated ideas. Did you get that sense from these excerpts too?
Absolutely. He starts by talking about resistance, something, we typically associate with friction and heat, right?
Right, like when you rub your hands together.
Exactly. But Feynman, he throws a curveball. He connects it to radiating energy, uses the example of a radio antenna releasing electromagnetic waves.
Okay.
That release, that loss of energy from the circuit, acts remarkably like resistance.
Okay, so it's less about the physical material and more about the energy being transferred, or rather lost from a specific point of view.
Precisely. And this sets the stage for Feynman to challenge another assumption we might have, that a charged atom, free from any friction, would just keep oscillating forever.
Intuitively, that makes sense. If there's nothing to slow it down, why would it stop?
Yeah. It's a fascinating thought experiment, and it leads us to the concept of radiation resistance. And this intriguing Q factor, which measures how many oscillations an atom can actually undergo before it loses its energy due to radiation.
And how many oscillations are we talking about here?
For a radiating atom, it's on the order of 10 to the power of 7 oscillations, which might seem like a lot.
Wow.
But remember, we're talking about atomic processes happening incredibly fast.
Yeah.
That translates to a mere 10 to the power of -8 seconds. This fleeting lifespan of an oscillation is directly related to the width of spectral lines we observe, a seemingly small detail that underscores the profound connections Feynman effortlessly weaves.
Yeah, it really highlights the interconnectedness of these seemingly abstract concepts with the very fabric of our universe. Even something as seemingly simple as the color of light.
Absolutely. Speaking of light and its wave-like behavior, Feynman then dives into the fascinating world of interference, where waves interact to either amplify or cancel each other out. It's a fundamental concept, but Feynman, as always, adds a layer of nuance.
I'm all ears. What's the Feynman twist this time?
Well, he points out that this interference isn't always so easy to observe. He uses the example of 2 radio oscillators that are slightly off in their frequencies, causing their phase difference, their timing, to constantly drift.
So it's like trying to watch 2 waltzing partners who are perpetually out of sync.
Exactly. It's a constant shift. And just like our eyes would average out a light flickering too fast, our instruments, and even our perception, can miss these rapid interference patterns.
So does it mean it's not actually interfering, or are we simply not equipped to perceive it in those scenarios?
It's a question that forces us to confront our assumptions about observation and measurement. Feynman masterfully uses these thought experiments to highlight the limitations of our perception and the importance of understanding the underlying principles at play. And this leads us to another captivating phenomenon: why the sky appears blue.
Okay. I have to admit, I'm always fascinated by the science behind everyday things. What's the answer? Is it simply a trick of the light?
You could say that. It all comes down to a phenomenon called scattering. Feynman explains that air molecules are essentially scattering light in all directions, but they're much better at scattering shorter wavelengths, like blue light, than longer ones, like red.
And that's what we perceive, that scattered blue light reaching our eyes from every corner of the sky. It makes you look at a clear sky with a new appreciation, doesn't it?
Absolutely. It reminds us that even in the vast expanse above us, it's the subtle interactions of light and matter that paint our world with color.
Speaking of color, how does this scattering principle explain those stunning red and orange hues we see during sunsets?
It's the same principle, but with a twist. During sunset, sunlight has to travel through a greater thickness of the atmosphere to reach our eyes compared to when the sun is higher in the sky.
Because the sun is lower on the horizon, right? The light has a longer path through the atmosphere.
Precisely. And because that light is traveling through more air, more of those shorter wavelengths, the blues and greens, get scattered away. What remains? The longer wavelengths, those beautiful reds and oranges.
It's like a cosmic filter. removing the blues and leaving behind those warm, fiery colors. It's amazing how one concept, scattering, can explain such different yet equally breathtaking phenomena.
It's a testament to the elegance and universality of the laws of physics. But this leads to a rather intriguing question. We've established that air molecules scatter light, but why don't we see water vapor in the atmosphere before it condenses into clouds? Why don't we see a hazy sky full of scattered light, even on a seemingly clear day?
It's like you're pointing out a blind spot in my understanding of how scattering works. If those water molecules are up there all the time, why aren't they constantly scattering light and making the sky look hazy, even on a clear day?
Yeah, it's a brilliant question.
Thanks.
And it hinges on the fascinating relationship between the size of those scattering particles, the water molecules in this case, and how intensely they scatter light. Individual water molecules are incredibly small, and while they do scatter some light, it's not enough for our eyes to perceive.
So it's like trying to notice a single grain of sand on a vast beach.
Exactly. But here's the crux of it. When those individual water molecules begin to condense, forming those larger droplets that eventually become clouds, their ability to scatter light, well, it increases drastically.
So it's not just the presence of water vapor, but the scale at which it clumps together that makes all the difference.
Precisely. And Feynman illustrates this beautifully by drawing a parallel between the scattering from a single atom versus a cluster of atoms. When atoms are packed closely together relative to the wavelength of light hitting them, their scattering becomes much more coordinated and intense.
So it's like the difference between a whisper and a shout. The individual voices of those water molecules only become noticeable when they're unified in a larger droplet.
A perfect analogy. And this collective scattering is what allows us to see clouds. Those water droplets have reached a size and a density where their scattering of light becomes powerful enough for us to perceive.
It's fascinating how something we often take for granted, like looking at a cloud, is governed by these fundamental principles of light and matter. And to think it all goes back to the size of those tiny water droplets.
Yeah.
It's amazing.
It really highlights how scale plays such a crucial role in physics and how our perception of the world is shaped by these subtle interactions. And it also explains why clouds generally appear white or grayish, even though we know blue light is scattered more effectively.
Because once those droplets reach a certain size, they're essentially scattering all wavelengths of visible light, resulting in that white or grayish appearance, right?
Exactly. But while we're on the topic of scattered light, there's another fascinating aspect Feynman touches upon in these excerpts: polarization. It's essentially the direction in which light waves vibrate, and it plays a crucial role in how we perceive the light around us.
I have to admit, when I hear the word polarization, I mostly think of sunglasses. Is that related to what we're talking about here?
It absolutely is. But before we get to that, let's unpack what polarization means in the context of light waves. Think of a typical beam of light, say sunlight streaming through a window. That light is considered unpolarized, meaning its electric field is oscillating in all sorts of random directions.
So it's a bit chaotic.
You could say that. But when that light is scattered, like by those air molecules that give us the blue sky, something interesting happens. It becomes polarized. This means the electric field of the scattered light starts oscillating in a more uniform direction.
So the scattering, in a way, tames that chaos and imposes a bit of order on the light waves.
Exactly. And we can actually observe this polarization using a special type of material called Polaroid, which is what those polarized sunglasses are made of.
Okay, now I'm really curious. How does a simple pair of sunglasses allow us to see this otherwise hidden property of light?
It acts as a filter, only allowing light waves vibrating in a specific direction to pass through while blocking those oscillating in other directions. Think of it like a gate, only letting certain vibrations through.
So when we look at the sky through polarized sunglasses, we're essentially seeing the effects of this scattered polarized light. We're removing some of that visual noise.
Precisely. And the extent of that polarization, how much light is blocked or allowed through, can vary depending on the angle at which you're viewing the sky. It's why those polarized sunglasses are so effective at reducing glare, especially off horizontal surfaces like water or roads. They're filtering out that strongly polarized light.
It's incredible how much we can learn about something as seemingly simple as light just by digging a little deeper, using these tools to reveal its hidden properties.
Absolutely. And Feynman, as always, nudges us to look beyond the surface, to question our assumptions, and to appreciate the elegance and complexity woven into the very fabric of our universe.
It's like those polarized sunglasses are giving us a superpower. revealing a hidden layer of light we wouldn't otherwise perceive. It makes you wonder what other secrets are hiding in plain sight.
And that's the beauty of Feynman's approach. He unveils these hidden layers, these seemingly counterintuitive aspects of the universe in a way that sparks curiosity, rather than confusion. For instance, remember how we talked about the size of water droplets and how it affects their ability to scatter light?
Right, the bigger the droplet, the more intensely it scatters light, making those clouds visible. But I do recall Feynman hinting that it doesn't just increase infinitely, right?
Exactly. It's easy to assume those clouds would just keep getting brighter and brighter as those droplets grow, but there's a limit. And this circles back to the concept of interference.
Because for those atoms to scatter in sync, to create that amplified effect, they have to be close together relative to the wavelength of light hitting them. It's like our choir analogy. If you spread the singers too far apart, their voices won't harmonize as effectively.
Precisely. And the same principle applies to those water droplets. When a droplet gets large enough, and we're still talking incredibly small, on the order of the wavelength of light itself, the atoms at opposite ends of the droplet are no longer scattering in sync.
So the timing is off. It's like some parts of the droplet are scattering blue light while others are scattering red, and the whole effect gets muddled.
Exactly. And this effect is even more pronounced with longer wavelengths, which explains why, even though blue light is more readily scattered, large clouds don't appear intensely blue to us.
Because those longer wavelengths, the reds and oranges, are also being scattered as those droplets grow larger. It's all about scale and how these seemingly separate concepts are, well, interlinked.
And Feynman, being a master storyteller, uses a rather ingenious example to illustrate this. An experiment with sodium thiosulfate and sulfuric acid.
Okay, now you have my full attention. Walk me through this.
When you mix these two chemicals, something fascinating happens. You get a precipitate of tiny sulfur particles forming in the solution. At first, these particles are incredibly small, and they scatter light with a slightly bluish tinge, just like our sky.
Because at that small scale, they're scattering those shorter wavelengths more effectively.
Exactly. But as more and more sulfur precipitates out, those particles grow larger, and the scattering intensifies, shifting the color we observe from a faint blue towards white. That's because those larger particles are now effectively scattering a broader range of wavelengths.
It's like those sulfur particles are transforming from a lone flute into a full orchestra, with all the different wavelengths joining the performance as those particles grow.
What a wonderful way to put it. And it doesn't stop there. As those particles continue to grow, they begin scattering so much light that it actually affects the light passing directly through the solution.
Meaning, what happens to the solution itself?
It starts to take on a reddish hue. Because those larger particles are now scattering away more of the shorter wavelengths, the remaining light, richer in those longer wavelengths like reds and oranges, passes through, giving the solution that reddish color.
It's the sunset effect happening right there in a beaker.
Precisely. And it all goes back to those fundamental principles Feynman so carefully laid out. The interaction of light and matter, the role of scattering, and how scale influences our perception of color.
It's incredible how these concepts, which might seem like abstract physics at first glance, are actually woven into the everyday world around us, from the sky's brilliant blue to fiery sunsets, and even those captivating chemical reactions happening in a lab.
It's a testament to the power of observation and the beauty of uncovering these hidden connections. And Feynman, with his infectious curiosity and clear explanations, guides us on that journey of discovery.
Leaving us not just with a deeper understanding of the physics of light, but also with a renewed sense of wonder about the world around us. He doesn't just give us the answers. He empowers us to ask better questions.
And that's perhaps his greatest gift, the ability to spark curiosity that extends far beyond the pages of his lectures.
And as we've explored today, that curiosity can lead us down some truly fascinating paths, revealing the elegance and interconnectedness of the universe, one scattered photon at a time. So the next time you find yourself captivated by a vibrant sunset or pondering the vastness of the blue sky above, remember those tiny particles, those oscillating atoms, those hidden principles of light and matter that orchestrate the symphony of color we call our world. Until next time, keep asking those questions and keep exploring.